Hello and welcome back to math class. The distance from a point to a line. The distance from a point to a line in 2 space. Well, there's a formula for that. The distance from a point P, an external point that we know, P naught, x naught, y naught, to the line with equation ax plus by plus c equals 0 is given by the formula. Distance is, now the numerator here is an absolute value of a number. This is not the magnitude of a vector. It's the absolute value of a number. A times x naught plus b times y naught plus c from the equation of the line and the known point. And the denominator is the square root of a squared plus b squared. And the development of this formula is in the textbook on page 534. But let's use it. Find the distance between an external point and a given line. Well, I've graphed the line. Now, if you think about it here, this would be when we drag 2x across and divide by 3, the slope of the line would be negative 2/3. And we can see that, yes, if I pick a point, say here, it drops 2 and runs 3. So yes, the slope is negative 2/3. And if I drag the minus 6 over and divide by 3, we can see that, yes, the y-intercept would be 2. And yes, the y-intercept is 2. So this is the equation of the line, and this is the external point P, negative 6, 1. And we seek this straight over distance, the right-angled distance. So our solution is to sub into the formula, and that was the formula given. And we just plug in all the numbers. A and B will be 2 and 3. There they are, 2 and 3. X naught, y naught will be, well, minus 6, 1, so there they are. And plus c here is minus 6, and this is the square root of a squared plus b squared, which is 2 squared plus 3 squared. And it's pretty straightforward. And we notice the numerator is the absolute value of a number. And so that would be positive 15 over root 13, which is about 4.2. Find the distance from the point to a line, but this line is not in our familiar form. We need it in the form ax plus by plus c equals 0 in order to apply our formula. So our solution will be convert to Cartesian form. And there was 2 methods for this. Method 1 was solve for the parameter twice and equate. And method 2 was sub the point and the slope into the slope formula. Well, we could get the slope from here. Remember, denominator is first, so the slope here is 5 over minus 6. But let's use method 1. So let's do method 1. Solve for the parameter twice. So this says x equals 3 minus 6s. Solving for the parameter, leaving x positive and dragging 3 and dividing by minus 6. And we see that y equals minus 2 plus 5s. Again, solving for the parameter by dragging the 2 and dividing by 5. And so now we have these 2 expressions for the parameter s, so we can equate them, cross multiply, and put the line into the format that we needed. We have the Cartesian form of the equation of a line. It used to be called the general equation. And now we can use it in the formula. And the formula was absolute value of a number here, ax naught plus by naught plus c, over the square root of a squared plus b squared, which will be 5 squared plus 6 squared. Plugging it all in, evaluating it, and we get 57 over root 61, which is about 7.3 units. Fairly straightforward. What's needed is that you can remember the formula And you can remember how to turn a line into the Cartesian equation. Solving for the parameter twice and equating works pretty well. Find the distance between two parallel lines. Well, we know these lines are parallel because they've got the same normals here, 3 minus 5. And so our solution method will be find any point on either line and then use the formula to get the distance from that point to the other line. On line 2, now there's many ways to do this. I just said, okay, how about on line 2, let's let y be 0, and so x is, we can see, 3. And so line 2 must go through the point where y is 0 and x is 3, so 3, 0. And sub that, and use this line and the formula together. The distance is the absolute value of a number, a x naught plus b y naught plus c over the square root of a squared plus b squared. And evaluating. And we have the distance between parallel lines. How about 3 space? Okay, this whole operation can be carried out in 3 space as well, with the possibility of skew lines and parallel lines and lines that meet at a point. The distance between a point, an external point, to a line in 3 space. This distance from the external point P naught, x naught, y naught, z naught, to the line to which it is external, line R, and I've given it here in the vector form of the equation, which is the only way to give the equation of a line in 3 space. And the distance here between the external point and the line is given by d is equal to, now, this is not the absolute value of a number. This is the magnitude of a vector. So it's kind of the same and kind of different from 2 space in that it's we got these absolute value brackets, but in this case it's the magnitude of a vector, and the vector is the cross product between the direction of the line and the vector qp, where p is the known external point from which we are measuring the distance, and q is any point on that line. And r0 here is a pretty good choice for that. And this is all divided by the magnitude of a different vector, the magnitude of the direction vector of the line. So one has to learn this formula. For 3 space, the magnitude over a vector over the magnitude of a vector. For 2 space, it was the magnitude of a number over the square root of, well, actually the magnitude of the normal square root a squared plus b squared. Okay. This formula is developed in the textbook, and math people care where formulas come from. Example, find the distance between a point which is external to a line. And the line is given as 3, 6, minus 5, which is a point, plus the parameter s times 4, minus 1, 2. And I've provided the formula we'll use here from the previous. Solution 1, which is the quick and easy way. Just sub into the formula, but we'll need to prepare this numerator first. So we'll need to prepare this cross product. Well, we'll need to prepare QP first of all. So we'll use Q being this point which is on the line. Remember, Q is any point on the line. Let's use this one. It's very convenient. So QP will be, well, P is the external point. And so QP is 8 minus 3, which is 5, negative 7 minus 6, which is negative 13, and negative 2, subtract negative 5, which is the number 3. And so we have our QP. So we've got this little bit of our formula. Now we've got to work on this cross product. M is the direction of the line, so we'll work out that cross product. 4 minus 1, 2, crossed with QP. And work that out. Now we have our numerator. So we'll need the magnitude of this vector divided by the magnitude of this vector, and that will be the distance. So it's a large square root sign, 23 squared plus minus 2 squared plus minus 47 squared over the square root of 4 squared plus negative 1 squared, which is positive 1 squared, plus 2 squared, and work that out, reduce it, it's a fraction, and we have our distance. The distance from the point to the line is about 11.4 units, which is what you get when you turn this into a decimal. Now I said this is solution 1 because there's another way to do this which is pretty important. So we shall do it the other way as well, but I'm going to place down here in the corner of the screen our answer so that you can confirm that yes, the second solution develops this same answer. It just develops it in a different way. So how did this way work? We worked out the numerator of our formula by figuring out this cross product first, which meant that we had to find QP first. So QP was Q is any point on the line, P is the external point, figure out QP, figure out the cross product, sub into the formula, and we get the distance. But there's a different way. Now for the second way. Solution 2. This way is useful because this way provides the closest point on the line as well as the distance to the line. So to do this, we let Q be the general point on the line. So we can put the line into parametric form and just use the coordinates as the parametric expressions. 3 plus 4s, 6 minus s, and minus 5 plus 2s. And then we'll reason that from the external point to our closest point has to dot to 0 with the direction of that line, because the closest point on the line is the one that forms the right angle. So the shortest distance will be the perpendicular distance. So Q is the general point on the line. P is our external point. So QP will be 8 subtract 3, which is 5 minus 4s. Negative 7 subtract 6, which is negative 13 plus s, because remember, we're subtracting. Minus 2 subtract negative 5, which will be 3 minus 2s. So here's our QP. And we know that this has to dot to 0 with the direction of the line. So we'll dot it to 0 with the direction of the line. Here I am doing that, and we know how to do this. It'll be 20 minus 16s, etc. Plus 13 minus s. Plus 6 minus 4s. And it's a single equation, and it's a single linear equation. Solve it for s. And we have s is our fraction, 13 over 7. And we'll plug that back up in here for q, and we'll find the point that's closest. It'll be 3 plus 4s, but 4 times 13 over 7, which is 52 over 7. It'll be 6 minus s, so 6 minus 13 over 7, and negative 5 plus 2s, so negative 5 plus 26 over 7. Combine the fractions, and we have our closest point. So this is the closest point on that line to P. So all we need to do now is find the distance between Q and P. So now to find the distance between Q and P. Note, we cannot multiply this through by 7 because this is a point, this is not a vector. So to find the distance, by the way, I've carried the answer forward from before still. Now to find this distance, the magnitude of vector QP will be the square root of 73 over 7 minus 8, or we could subtract the other way, 8 minus 73 over 7 squared, plus negative 7 minus 29 over 7 squared, plus negative 2, subtract negative, so that'll be negative 2 plus 9 over 7 squared, and do the math here. I perform the operation of addition and subtraction of fractions first, squaring top and bottom in each case, adding the fractions under the radical, and then reducing the fraction. And we see that, yes, we got the same distance, of course, with the added benefit being that we know the point on the line that's closest to the external point. Our reasoning was PQ has to be at right angles to the direction of the line, because this Q is the one that forms the perpendicular. And that's why we dotted PQ with the direction of the line and equated it to 0.